Hey, hello everyone. Let's start today's discussion. So far, we covered and we discussed about the definitions of the root-Lucas method. We saw what it represents, how we can develop the root-Lucas graph, and how basically what are the shortcuts when we wanted to uh, draw the root-Lucas graph, and what are the properties and the rules that we have for the root-Lucas techniques and the graph that we develop by root-Lucas. Now, in the previous discussion, we mentioned that sometimes we don't have exactly the same number of the poles and zeros. So, for example, if we are short for the zeros, that means the trajectory of our poles as k increases, that gain increases, would go toward infinity. Okay? Now, for example, for a system, let's say have an example system here. We have a unity feedback loop, and our transfer function here is k times s plus 3, s plus 1, s plus 2, and s plus 4. Okay? Now, we already know how to find the place of the poles when we have the k equal to 0. Very good. So, the graph that we can draw that represent the place of the initial place of our poles could be found by the poles and zeros. So we have a pole at value s equal to 0. We have another pole at, let me draw the units, -3, -4, -5, 1, 2, 3. So we are going to have another pole at -1, okay? And another one at -2, another pole at -4, and we have a 0 at -3. Okay? So far, we learned how we could analyze the graph to kind of estimate the trajectory of those poles based on the value of the k when the k increases. We learned that the sections in the real axis that has odd number of the zeros and poles to the right of it would be the sections that basically has the trajectory of the root-Lucas on them. Are we good? So, the section from 0 to plus infinity doesn't have anything on the right of it, so this part of the real axis is not going to be included in our root-Lucas graph. From 0 to -1, we have one pole at the right, so this one is included. Correct? Here we don't have anything. This part is also included. We don't have anything here. And then we have this section in our root. Are we good? Now, we learned again is one of the properties that the trajectory of our root-Lucas, okay, would start from a pole and would end in a 0. correct? Now, in this middle section, it's very easy to find what is the trajectory, because we are going to start from this pole and end up to the zero. But these other three poles, they don't have a finite zero to basically move from those poles and end up on those zeros. We already said that when we are short, okay, we can assume that, okay, we don't have any finite zero for these three poles, okay, these extra poles. So we can assume that there is some zeros in infinity, okay, that these poles can end up on those zeros. Do you remember that? Now, before we simply approximate the trajectory, okay, with a linear kind of like behavior. So we said, okay, this pole, because it moves through this axis, okay, that means there is a zero on the minus infinity on the real axis, that this one would end up to that zero. And these two are going to move toward each other at one point they would collide, and one of them goes directly to the plus infinity and another one goes to the minus infinity, perpendicular to the real axis. Okay, but that's a very simplified analysis of the trajectory. The infinity doesn't exist on one point perpendicular to the real axis. It's all over the place. Every margin in R around our graph, when you move as like an infinite magnitude from the zero, is infinity. So who says that the zero of this pole is here? It might be here or here. Right? We don't know it. It is an infinite zero. We can't find it. It's conceptual rather than like mathematical. Okay? How we can find the trajectory of these poles that would end up in infinity, to find out, okay, what would be this line dynamic? Is it exactly like a perpendicular line, or it should have like a curve, like to the right, or even like a curve to the left? And if it has a curve, what is the kind of like the tangent line, the slope of tangent line for that curve? How steep is that curve, basically? Okay? We want to find out how we can actually find that exact trajectory. Today, we are going to find that, and how we can basically move around from the simple assumption of perpendicular lines to a more accurate situation. Now, in order to do that, we want to define the concept of asymptote lines. Okay? What is the definition of that? The asymptote lines is the line, okay, is the line that it would touch the curve at infinity. Because eventually we want to kind of like find out or estimate where is that infinite zero. Okay, so we are going to consider a line, for example, this is just a haphazard line, okay? So I'm going to consider like a line here, okay, that I assume I don't know what is the slope of this line or where it would collide with the real axis. Okay, so I don't know this line. It's an unknown line. But based on assumption, this line should touch the curve in K when K goes to infinity. Are we good? Now, what we are going to learn is how to actually find the exact values of a slope and the collision of that line with the real axis. So basically, we move from an unknown line to a known line, and we can define the trajectory based on that. Are we good? Now, based on the definition that we have, this line, okay, this line would collide with the real axis at a point that, let's call it delta. Okay? And this is a line, so this is the slope. But we learned that beside the ratio, we can show the slope by the phase angle. So it's also going to have a phase angle with the real axis, which we simply call it theta. And let me draw this here. So if we know the delta, and if we know the theta, okay, then we know the line. Now, using the properties that we learned previously, okay, what was that property? Every pole that we had, okay, the theta of that pole, the theta of any pole, including that one in infinity, right before we end up in that zero of infinity, okay, that pole in infinity should be, the theta of that pole should be 2k plus 1, 1/8. You remember that rule? Okay? And the magnitude, the k, the magnitude of the k on that pole, which is infinitely close to the zero in infinity, is going to be 1 over the magnitude of whatever g or gh that we have, whatever transfer function, let's say gh to be general, on that pole. Are we good? Those were the definition that we have, the criteria that we had to estimate if a point is pole or not. So if it's the pole, should follow these rules. Now, let's say we have a pole here in infinity. This is right before we end up at zero. What is the theta? This basically, the vector that shows this pole is going to be the same vector as this line. Correct? Because that line touches the curve on the infinity. So it is going to be the same point, okay, approximately, is going to be the same point with a very tiny, infinite small difference, okay? That means this line is going to be the vector that m theta, okay, that we learn to represent any complex number in a phasor domain with a vector. So it means the theta that happens here would also follow the rule that we had. Do you remember what was the rule? The summation of the theta zeros minus the summation of the theta pole would be that theta. Remember?
What you said?
Okay.
What you said?
the theta here, okay, is gonna be the summation of, like, you see, this is the point, okay? We had a vector from this pole to that, which has a theta 1, a vector from this point to that, theta 2, this 0, theta 3, this 0, theta 4. Remember that? Then we subtract the thetas of zeros and poles and find what is the theta, because eventually all together should end up in a odd multiple of 180. Are we good? Now, you can review the discussion that we have to remember what we talked about. Now, using those two rules, if we drive the whole mathematic, we can find out that the theta of this line, should be the basically the 2k plus 1 180, that condition, divided by the number of the poles, n is number of the poles, and let's say m is number of the zeros, okay? It's gonna be number of the poles minus number of the zeros. You can derive the mathematic. I want to move fast because we have a lot to cover. So the theta of that line is gonna be 2k plus 1, 180, n minus n. Number of the poles, number of the zeros. Now, we have a k, we have a value, okay? How we can find how many k that we should cover in order to find all the thetas of all the asymptote line. Okay, now, simply by looking into that graph, you could understand, or you could see that eventually we are gonna have these two poles leaving the real axis. So we are gonna have two asymptotes for those two curves. Okay, one line here, one line here. Are we good? This is the symmetric kind of a graph. And this one also leaves, so we are gonna have an asymptote for this pole too. Now, here we had the n here. Our number of the poles was 1, 1, 2, 3, 4, and the number of the zero was 1. We ended up with 3 lines. Anyone can guess how we can, in general formula, how we can find how many lines should we have in a general kind of like example. We don't know how many poles and zeros. We have n poles and m zeros. There is no numbers. Looking at this example, anyone can guess in general how many lines we should have as an asymptote line? In this example, we have 4 poles, 1 zeros, and we ended up with 3 asymptote lines. N minus n. Correct? The difference between the number of poles and zeros would define how many lines you should have in your curve. Okay, if we know we have 3 lines for this example, that means we have to start the k from the 0, and then what values we could have? Let me show this with another number. I don't want you to confuse you with that K that we have is there, not necessarily, let's say, D. One D is 0. Okay, then we can have D equal to 1, right? But this is a symmetric situation. So if we have a positive D, we should have a negative 1 too. Make sense? Is that clear? I want you to fully understand that. See, we have a theta. Because it's symmetric, we have a mirror line, which is minus theta. Correct? So whatever value of multiplication we have here, we also should have the minus one of that. Okay? So, plus minus 1. In this example, we have 3. We already have the 3 values that we need. Are we good? If we had more line, we would continue to plus minus 2, plus minus 3, moving all the way forward to cover the number of the line that we need. Is that clear? Now, in this example, we have 3, so we have 0, plus 1, minus 1. Now, let's put that in the formula. What will be the thetas? The thetas of this example, theta 1, theta 2, and theta 3. If we put 0, it is going to be 180 divided by 3, which is 60. So 1 theta is 60. If we put 1, it is going to be 3 times 180 divided by 3, which is 180. If it is minus 1, it is going to be minus 180 divided by 3, minus 60. So far, we know that the lines that we have, let me clear up a little bit here. It's too crowded. So far, we know that the lines that we have, one of them is 60 degree, one of them is minus 60 degree, and another one is 180. Very good. Now, we are not done yet. We don't know where these lines would cross the real axis. If we don't know that, we don't have any known line. We just know the direction of those lines. It could be here or here, So we need to know the point delta that we define in order to exactly know what are the lines are. Again, using those formula, you can drive the math. That delta, that point that those lines would cross the real axis, okay, can be found by the summation of the finite poles, which let's say poles, okay, minus the summation of the zeros divided by, again, n minus n. Okay. Now, what is, for this example, what is the summation of the poles? We have 0, -1, -2, which is -3 when you add it. Then we have -4, which means -7. So here we have -7 minus our 0 is the only 0. So it's -3, so it becomes +3 divided by n minus m, which is 3. So in this example, the delta will be -4/3, or -1.3333 all the way to infinity. Are we good? So where is that point? Forget about my estimation. It is not exactly, so it's gonna be -1.3, so somewhere like here. So our line should be starting from this point, -4/3, and 1 with the theta of 60 degree, 1 with the theta of -60 degree, and 1 with the theta of 180. Now, knowing that, now we can find the trajectory of our curves. Here, yeah, it is -4, number of the summation of the zeros. Okay, this is a minus. Okay, so -1, -2, -4 become -7. The 0 is -3, and we have another minus here, which is +3, and then we have our. Is that good? Now, any other question? Now we know our asymptote. The 180 line is very easy because it's gonna keep moving forward on the real axis, which we already know this one has the same properties. So this pole -4, is gonna move toward infinity, okay, in a way that in infinity, this line, this θ2 line, would touches the curve. Same goes for the θ1. θ1 is going to be the line that touches the curve in plus infinity. Good? So let's say we have infinity here. Let's say we move on and we have infinity here. That means the curve should forget about my bad drawing. Okay, so we start from this point. Let me try a better drawing. We start from the point of departure when the pole leaves, and the curve should touch the line in infinity. See, now we have a better estimate of trajectory rather than just perpendicular line going directly, like vertically to plus infinity. Are we good? Is that clear? Same goes for here. This line. We are gonna move all the way, so in infinity, these two lines would, this line and this curve would touch them. So now we have the trajectory, okay, a more accurate trajectory of our poles when k increases to infinity. Any question? Do we have any question? No? Okay. So far, we learned about how we can basically draw the root Lucas curve. But there are some information on that curve, okay, that is very important for us, okay, when we want to analyze the response of our system. Is that good? I hope I can, yeah. Anyone can guess what are those important points are? Like, for example, when you look at this graph, which I messed it up a lot. When you look at this graph, what type of important point in this graph you see that it could help us to analyze how our system would respond to different K or S, to different poles or states, whatever you want to call it. What are the important points? Two of them are very obvious. Anyone can tell me those two? We already talked about that before. When we wanted to like define a stable and unstable system. What is unstable system? Where this system is unstable?
To the right of, yeah.
When the poles are in the right hand side. So point out to the 2 points that are very important for stability analysis. We are unstable here and stable here. Which point is important for analyzing the stability of the system? Which point in our root Lucas graph? What's it? There is
origin.
0 is the reference. Okay. At what point the system gets unstable? Let me rephrase the question. No, look at this graph. At what point this graph gets unstable? What was the definition of unstable? What area was unstable?
I mean,
the right half side was unstable. At what point we get unstable? These are the trajectory of the poles. On which point the poles make the system unstable? On what K our poles become unstable? Come on, I'm really giving you a lot of information. Unstable part is right half side. Which K, at which point the K make the poles unstable, meaning the poles are on right hand side. Come on, this is the graph at right hand side. This portion is in right hand side. This portion is in right hand side. That means when the poles are moving here, are existing on this part of the curve, the system is unstable. So the point that distinguish the stability and unstability is when we cross the imaginary line. Are we good? So after these 2 points, let me show it with the square. After these 2 points, when we pass these 2 points, then we get unstable. So these 2 points are important because they are margin of between the stability and unstability. And if you remember, we call that marginally stable. Do you remember? Now, remember when we talked about the second order system, we said we could have different type of response. We could have an overdamp, we could have critically damped, or we could have some sort of oscillation, either a sustainable oscillation or a decaying oscillation. When what was the nature of the poles, okay, regarding the real number, complex number, which type of poles would introduce oscillation? Do the real values introduce oscillation? Like when the poles are in the real axis? Yes or no? How about the complex one?
Yeah.
Complex one would create oscillation, and the oscillation frequency was the imaginary part. You remember? So if we are anywhere but the real axis, that means we are going to have oscillation. On the imaginary line, we are going to have sustainable oscillation. That means it doesn't decay. Remember? Anywhere else, we are going to have a decaying oscillation. Okay? Now, look at these 2 points. Oh, sorry, this 1 point in this example. Knowing that, what is the significance of this point? What happens to poles on that specific point? These 2 poles move and collide, okay, and then continue their path as k increase on the curve that we draw. Now, what is the significance of this pole? This point. This is the point where the pole leave the real axis. So they change from real number to complex number. Does that make sense? So this point is the margin that after that, we are going to have oscillation in our system. Make sense? So these are important poles. Now, sometimes I want to raise this to give you another example, more general example. Are we good? Sometimes it's not just that the poles are leaving the real axis. We already saw that, I think, in one example before. Let me draw another example. Let's say we have this, and let me make the unit also clear: -1, -2, -3, 1, 2, 3, 4, 5, J, 2J, 3J, -J, -2J, -3J, and we are going to have a 0 at 5, a 0 at 3, a pole at -1, and a pole at -2. This is our root loops, or the closed loop poles and zeros. Okay, this is not the same as this. Let me erase this, so make sure we don't get confused. This is another transfer function. Now, let's try to actually draw this with Locus first, and then talk about the points that are important. For the properties, we know we are going to have a trajectory between these two poles on a real axis. Same here. The poles end up in zeros and start at poles, the trajectory. Very good. So somewhere here, we are going to leave the curve, and somewhere here, we are going to enter again the real axis. Okay, now we are not short for any poles or zeros. So these two poles that leave here would end up entering this portion of the real axis, right? So basically this would end up here, and this is a symmetric system. My drawing is bad, but this is like a signal, okay? Basically. Now, we have 2 points here. Let's call it delta 1. And here, let's call it delta 2. At delta 1, we are leaving the real axis. At delta 2, we are entering the real axis. Are we good? Now, look at these graphs. The point, first let me give you some terminology and definition. The points that we are leaving the x-axis or the real axis, we call it breakaway point. Okay? Breakaway point. The point that we entering is break-in point. Very straightforward naming. It's not, very confused. Now, how we can find those poles, those points that we are leaving and entering the real axis? We already know that the poles, the trajectory of the poles, that start at these poles when k is 0. So when k is 0, okay, the pole 1 is -1 and the pole 2 is -2. Are we good? Now, as we increase the k, okay, pole 1 would move away from -1, and also pole 2 again would move away from -2. Is that clear? We already know that. We start at the finite pole, the poles of our transfer function, and as we increase the k, we are going to move away from the poles, the starting point, and end up in zeros. Right? Now, I like to find this delta. So let me ignore the curves that are in the complex number and only focus on what's happening in the real axis. Okay? If these two move by increasing the k and collide at this point and then leave, that means when the poles are in the real axis, this point happened, this collision point happened when k is maximum, okay, before we leave. Correct? So the k at delta 1 is the maximum K before we leave real axis. Are we clear on that? So now here, what about delta 2? We said we are gonna end up at zeros when K goes to infinity. Correct? So here, K is infinity, here is also K infinity. So at this collision again point, we are ignoring the complex part, only the real axis. The K here should be less than all the other K's, right? Because we are in the real axis, we are gonna start from here and move away to the zeros. So here at delta 2, K is the minimum.
Tends to 0. It means tends to 0.
No, not 0. The 0 is here. Okay? We move and then we leave and then we come back to real axis. So K here is a number. We don't know. But it definitely is less than all the other numbers here because this is the trajectory when K is still increasing. Are we good? So how we can find the K when the delta 1 is leaving, basically is a delta 1, which is the leaving point, breakaway point, and the delta 2 as breaking point. What is the significance? What is the property of mean point and max point? At mean point and max point of any curve, the differential is 0. Are we good? So if we write the K as a function of S, okay, the function that describes the K based on the S's, if we put the K, the dk over ds equal to 0, the S's that satisfies that condition are the local mean and local max. Are we good? I don't want to say global because I don't know what's happening. But definitely they are local mean and max. Is that clear? Do you remember that from algebra or calculus? What we are talking about? If you have any question, let me know. No? Okay. Now, the function, the K G of S, H of S, for this specific example, okay, is gonna be K. What are the zeros? 3 and 5. So it's S minus 3, S minus 5. I'm using this example because the general formula is too complicated for explaining. And the poles are -1 and -2. So we have S plus 1, S plus 2 as the poles. Are we good? We know these two deltas are poles. So they should follow the properties of the poles, which one of them was the K times G of that delta, whatever, which, it doesn't matter which one, H of delta should be 1, should be 1, or minus 1. Are we good? Do you remember these poles are the poles of 1 plus kgh? So kgh should be equal to minus 1. Now, so K is minus 1 over G of delta, H of delta. Very simple. So now I have the function that describes K based on those deltas. You can also put S, doesn't matter how you name it. Now, the GH is this part without the K. So in this example, my K is minus 1 over, I'm going to use delta. So delta minus 3, delta minus 5 over delta plus 1, delta plus 2. Which is, basically, if you run the calculation, it's going to be minus delta squared plus 3 delta plus 2 over delta squared minus 8 delta plus 15. So this is going to be the function that describes my K based on those poles. We said the max mean values is when the differential of this function is equal to 0. So what we need to do is to make a differential, calculate the differential of this function in respect to that delta. So the differential of the K in respect to delta, this is kind of like the differential of f over g prime, which is going to be f prime g minus g prime f over g squared. Okay? Probably you remember that from the properties of a differential. So you know how to make a differential. It's a little bit tricky and challenging, but you know how to do that. If you do that, you are going to find out that the differential is going to be 11 delta squared minus 26 delta minus 61 over delta squared minus 8 delta plus 15 all squared. And we want this one to become 0. If this one to become 0, that means the denominator should be 0. Are we good? And if you calculate the zeros of the denominator, okay, here, we could calculate that. You are going to find out that the delta 1 and delta 2, let me not name them first. The deltas are going to be minus 1.45 and 3.82. So simply by looking at it, you can see that the delta 1, the departure point, the breakaway point is minus 1.45, right? And the delta 2, the break-in point, is 3.82. Are we good? How we find those?
Can you walk your next time?
Again, when you look at the trajectory, we know the poles start for k equal to 0 And as k increase, they move toward the trajectory that we have. So the point before they leave the real axis would be maximum k of the trajectory on the real axis. Are we good with that? Is that fully clear? What we're talking about? K would increase, that means this K is bigger than the before, this one is bigger than all the befores, so this one should be bigger than every K before that. So we have a local max here. Same analogy, we know that as K increase, we move towards zeros. So this K is bigger than the previous one, this is bigger than the previous one, so that means the point that they enter the real axis is the lower k that we are going to have on the real axis. So this is a minimum, the local minimum. Now, the properties for minimum and maximum is the differential of the values, the variables, should be equal to 0. We already know that. So what we have to do is we want to find the max and mean of k. So we need to find the function of the k based on these points, based on the SS or whatever you want to call it, deltas. Okay, so this is our transfer function. We developed that based on the poles and zeros in the graph. So we know the poles are the poles of the denominator of the closed loop. The denominator of the closed loop was 1 plus kgh. So kgh should be equal to -1. That means k is equal to -1 over gh. So now we have a function of k based on the deltas or s's.
Wait, where's the -1?
The root locus, okay, was the trajectory of the pole when we had a closed feedback. Remember that? That was the definition. So here we have kg and here we have h. Remember? So the closed loop would become kg over 1 plus kgh. The whole system. The poles of this system are the zeros of the denominator. So this 1 plus kgh is 0. That means kgh should be equal to -1. So we have the function of the k based on the g and h. Now we need to find the local mean and max, which is when the differential of that function becomes 0. Very good. So we make the differential of this function. For this example, our gh was s minus 3, s minus 5 over s plus 1, s plus 2. We put that here. Okay. And then we calculate the differential of that function. You can do that is f prime g minus g prime f over g squared. When f is the denominator and g is the denominator. We good? Now, we calculated the differential. Now, our condition was the differential should be equal to 0. So whatever delta that makes the differential equal to 0 should be the mean local and max local of the k, right? So we solve this condition, which means the denominator should be equal to 0. It's a second order system. We know how to solve it. We find the deltas that makes this function 0. So we have the breakaway and break-in point. Now, how you can find out which one is the break-in and which one is the breakaway. It's very easy. It's based on your graph. So this one is minus 1.45, so it should be here. So that's the breakaway.
Breakaway.
Breakaway. The other one is very simple. It's break-in. Are we good? Is that clear now? Let me know if you still have question on that. Now, let's learn a little bit easier way and kind of like get a trick that would help us to avoid the whole situation of finding the k function and the differential of the k function. The trick is, are you okay? I want to erase that. The trick is, if we develop the function of the delta, which says the summation of delta plus zi is equal to the summation of 1 over delta plus pi. Now, I want you to like pay attention. Zi, this is very important. Please pay attention. Zi is minus zeros that we have. Pi is minus poles that we have. Okay? For this example, our zeros, the zeros are 3 and 5. So our zi is going to be, this part is going to be 1 over delta minus 3 plus 1 over delta minus 5. Are we good? Now, if you are a little bit confused about that, remember the term that creates this 0 was s minus 3. Are we good? So, delta minus 3. Delta minus 5. Same goes for the other side. 1 over delta plus 1 plus 1 over delta plus 2. Are we good? Now, you can find the function that describes, if you simplify that, this is a second order function here. This is a second order function here. So basically that one become 1 over delta square minus 3 minus 5 minus 8 delta plus 15. Are we good? The other one become delta square plus 3 delta plus 2. Right? Now, you can simplify that. So this one become delta square plus 3 delta plus 2. And this one become delta square minus 8 delta plus 15. Are we good? Did I make it right? No. No, that is not right, because here we also gonna have delta minus 5 plus delta minus 3, and here we are gonna have delta plus 1 plus delta plus 2. Now we're good. Is that Make sense what we did? Okay, now, if you multiply these two and these two with each other and move one side to other, you are going to end up on 11 squared minus 26 delta minus 61 equal to 0. Is that sounds familiar? That one is the denominator of dk over d delta. So that condition would also satisfy this condition. Make sense? So this is a shortcut for finding this function without getting a differential. Are we good? So solving this function would give you the data that would describe the break-in and breakout. Breakaway and break-in. Sorry. Any question?
So I did taking the derivative. Sorry. Wait, what function you were taking the derivative of?
The k function. Okay? The k function was we solved, we said, okay, k gh should be minus 1.
Oh, yeah.
Okay, so k is minus 1 over gh. This is a function of the s's. You can replace the s's with the delta. We want to find delta, which is one of the s's. Are we good? So now you have a k as a function of those deltas. We took a derivative. We solved for the deltas that make the derivative equal to 0. That was the mathematically sophisticated way. Now the shortcut is you can have this formula, which is the summation of 1 over delta plus zi, when zi is the minus value of the z's, equal to sigma of 1 over delta plus pi. The p is minus value of the poles you see in the graph. You run the mathematical derivation, and the formula that you would end up, if that is equal to 0, is going to be the same condition as that derivative equal to 0. So the roots of this function is the same roots that make the differential equal to 0. Are we good? There is another way, which is a very kind of like, I don't want to say silly, but it takes a lot of time to solve. And that's, if you remember, the first method that we tried to find the trajectory of the poles was to actually put the number for the case and find where are the poles. Do you remember the example? So we put the k equal to 0 and then 1 and then 5. And by that, we solved what's going to happen to the poles. Okay, for each k, we solve the poles of that transfer function, kgh. Okay, and we find out what is the trajectory of the pole. Now, the same way, you can assume the poles. Let's say we have minus 1, we could have minus 1.1, and find what is the k for that. If s is equal to minus 1.1, you know how to find the k. It's the absolute value is the amplitude of this 1 over gh when s is equal to that 1.1, minus 1.1, right? We already learned that. So you can calculate the k. Then you start another point, 1.4. Again, you calculate the k. When you have the table, you can find the trajectory of the k. Where the k is maximum is a local maximum. So the k would increase, and at a certain point, it'll start decreasing. Are we good? then you can find the maximum and minimum. It's not a very efficient way to find that. This is the best way. Now, finding, we said these break-in and break-out, breakaway and break-in points are one of the important parts of the system. But we said we have two other points where the trajectory crosses the imaginary line, because that was the margin of stability and instability. So we need to find those points too. Okay, now how we can find those poles is, again, it's very easy. The trick is you have the transfer function. Let's say an example is that T of S is equal to AS plus 3 over S4 plus 7S3 plus 14S squared plus 8 plus KS plus 3K. We have a very complicated transfer function, which is not the transfer function of this graph, okay? We want to find out where the trajectory of the poles for that transfer function would crosses the imaginary line. The trick is, first, you would develop the Routh-Hurwitz table. You already know. We already covered that before. So we are gonna create, let me do that over there, create the Routh-Hurwitz. This is fourth order, so S4, S3, S2, S1, and S0. Okay, now we know how to do that. I'm gonna move forward very fastly because we are running out of time. So the Routh-Hurwitz of this the specific function is gonna be this way, minus k squared minus 65k plus 720 over 90 minus k, and this 0 is 21k. This is the Routh-Hurwitz of that transfer function. Now, if we want to find the k that would cause the trajectory to cross the zero line, the imaginary line, we have to find a row that we can create the row all the way equal to 0. So we wanted to find which of these rows we can have a k for it that the whole row becomes 0. Here we can have, because we have constant number, here we have constant number, we can make these two rows 0. This one becomes 0 when k is 0. That means it won't work. And 90, that makes this one 0, won't work for this one. So this is also cannot be 0. Let's try this one. This one is the second order, so we can't find the k that makes this one 0. We have to solve for the roots of the denominator. So if we do that, we would find, if you solve that, we would find for k equal to 9.65, we can make this one 0. Are we good?
What is it? No,
Sorry?
what number?
That's
This
No, the
720.
720. Sorry. Let me. Now, we find the k that makes this 0. We move one line up. This is S1. We move to the S2, and we create the function describing by this row. Remember, that function would be 9d minus k times s squared, okay, plus 20k. 21K. You remember how we did that? This is S squared. First one is a multiplication of the S squared. Then we skip one order. So we skip S1. The next one would be the coefficients of S to the power of 0, which is 1. So coefficients of S squared plus coefficients of S to the power of 0, which is 1. Is that clear? That was the root service. Each point, the next point, we skip one order, and then we have the coefficients of the next parameter. Now, we put the k that we find into that function. So if you do that, this one become 80.35 times S squared plus 202.7. And we try to find the roots for that. Are we good? Now, the roots of this function are the point that we cross the imaginary line. In this example, the S's are going to be plus minus J 1.59. Very easy. So, for K after that, we're going toward the instability. For S's after that, we are unstable. Make sense? So, in this example, we need to make sure that K would not go over this number. Otherwise, we lose the stability. Any question? Any question?
I guess K is just describing on like what point in the real axis where the system becomes stable. And so S is also describing at what imaginary points.
This is what happened. This is your plot.
Yeah.
You can have some sort of trajectory, whatever it is. Okay. If you move from the left to right, you get unstable. These points define the margin of that. To find these points, you do this. For this example, these margin are J1.59 and minus J1.59.
Mhm.
And these poles happen in the trajectory when the K is 9.65.
Okay. And that would be your max K.
That would be your
Yep.
max
Yep.
K.
Okay.
Okay, so if you're designing a system, I don't know what K would represent in your actual system. It could be a resistor or a capacitor or anything. Okay? Or in a mechanical system, it could be like a characteristic of a spring. Okay? That K should not go over 9.65. Otherwise, your system gets unstable.
Okay, gotcha.
Are we good? But if you don't have any question, this is for today. I'm sorry I passed the time. And no question? Have a great rest of the day.